So the plan for today is I'm going to discuss with you the sort of broad understanding of what we in the field think dark matter actually is, what we don't know about it, and I'm going to walk you through all the way to the stuff I'm working on at the moment that I'm thinking about as we speak. Let me begin by making the case for dark matter. So I want you to imagine that you're part of a jury and that I'm going to present to you evidence for why I think dark matter is there in the universe, and then you can make up your own judgment at the end of the day. So first of all, let me tell you what we know about dark matter. First of all, we know that it's a form of matter that does not emit light. Okay, that's why we think about it as dark. It does not interact with ordinary light, does not emit light, does not absorb light. It moves very slowly compared to the speed of light. So in the jargon, we say that it's cold. Okay, so it's a form of dark matter that's moving relatively slowly compared to the speed of light. We know that it makes up a significant fraction, almost 1/4 of the total mass energy budget of the universe. And in fact, that is 6 times more than ordinary matter. So you see on the pie chart, and here I'm not going to go through the details of this, but from combination of the cosmic microwave background on the left side and our measurements of the relative abundance of light elements, that we know that the composition of the universe is given by this big pill, which is about 3/4 of dark energy, stuff which is making the universe accelerate today. That's not going to be the subject of this discussion. Dark matter, which is roughly 1/4, and finally ordinary matter, which only makes up 5%. So the stuff we're made of only makes up 5%. So we know this. Now, the first piece of evidence, perhaps one of the key hints that dark matter is around, is when we look at galaxies. So here's a very short discussion of what a galaxy is. What you see here is a spiral galaxy, a quite massive galaxy. So galaxies in general tend to have a mass between 10 to the 8 to 10 to the 12, the mass of the sun. And the size of it is about 100 light years. Okay, this varies from galaxy to galaxy, but these are numbers you can keep in your mind. Now, what is the hallmark of dark matter? Let's do a little warm-up to start with. Let's think about the solar system. So in the solar system, most of the mass is, of course, concentrated in the sun at the center. And what you see in the motion of planets is basically Kepler's third law. So you see that the planets which are closest to the sun rotate faster around the sun. You see Mercury very nearby, which is spinning the fastest, and the outer planets are moving more slowly. So in other words, when the mass is concentrated near the center, what you expect if you were to show the velocity of the planets as a function of how far they are from the center, you see that it sort of monotonically decreases as you move further out. So in other words, now if we apply that logic to the galaxy, here's the galaxy. Again, most of the mass, much like in the solar system, is concentrated near the center. And so what you'd expect if there were no dark matter is indeed what you see here. So stuff near the center is rotating quite fast, but as you move further out, things are moving quite slowly, much like the planets. What we see instead is this, okay? And you see what you see is that as you go further out, the stuff further out is actually moving along pretty rapidly. In fact, it's moving along much more rapidly than you'd expect just based on the amount of matter that we see. So as a curve, what is plotted here on the left side, this curve there is the velocity, again, as a function of distance. You would expect it to fall off as you move out. What you see is, in fact, that the velocity flattens out. As you move out, everybody has the same velocity. So therefore, what we imagine is that galaxies are surrounded by a dark matter halo that is doing this additional pull to make visible matter rotate fast. All right, that's piece evidence number 1. All right, members of the jury, let's move on. Piece of evidence number 2 are galaxy clusters. So galaxy clusters are wonderful objects. They're the most massive bound objects in the universe. So there are clusters of galaxies. They contain many galaxies. The mass of the most massive clusters range from about 10 to the 14 to the 10 to the 15 solar mass, okay? And their size is 3 million light years. So huge objects. Despite the fact that we call them galaxy clusters, in fact, it's a little bit of a misnomer, because in fact, galaxies themselves only make up 1% of the total mass of a cluster. The cluster is such a massive object that there's a lot of gas actually just moving around. Ordinary matter in the form of gas moving around at quite high speed, and that makes up actually 10% of the total mass of the cluster. And finally, dark matter makes up the rest, okay, we think. So in galaxy clusters, we also imagine that there is a halo, a dark matter halo within the cluster. And one way we see it, again, is one way to see it. The first piece of evidence is that galaxies and clusters themselves move much more rapidly than they should if there were no dark matter. And second of all, you can also watch the gas. The gas is moving so rapidly it emits radiation at a very high temperature. So both of these things tell us there's dark matter. Piece of evidence number 3 is gravitational lensing. So Einstein taught us that in the presence of gravity, everything should basically fall, or should be influenced by gravity, including light. So not just ordinary matter falling towards the Earth, but also light should be affected, the motion of light should be affected by gravity. And this we observe in the form of so-called gravitational lensing. So here in this video, what you see is as I include a galaxy cluster, you see that light emanating from a background galaxy is bent as it comes to the Earth. And at the end of the day, in this particular case, the bending is so strong that you see multiple images of this background galaxy. At the end of the day, you see there are 2 images. So it acts, the dark matter in the galaxy cluster is acting like a lens for light. Another piece of evidence related to lensing, but in some sense gives you an even more direct vision of the dark matter playing a role here, is this bullet cluster. All right, so let me tell you a little bit about the bullet cluster because it's a fantastic object. So in the bullet cluster, what you see is the aftermath of 2 clusters colliding together. The cluster, remember, has a lot of gas in it, and so if you collide 2 clusters together, the gas will be slowed down by, the forces that gases feel, okay? So the gas you'd expect will be slowed down during the collision, and this gas is observed here and is shown as the red spots. Dark matter, on the other hand, doesn't interact very much. So you'd expect it, in fact, dark matter interacts so weakly, you can think of it as just interacting to gravity. It will fly through during the collision and end up being segregated from the gas because it's not slowed down by the same interaction that gas is. This is shown here in blue. Blue is meant to represent dark matter. The observation that we do is, again, gravitational lensing. So what you see here, the key piece of evidence, is that, remember, most of the mass in ordinary matter of a cluster is in gas, okay? And the gas is in red, whereas the mass, which we observe indirectly through gravitational lensing, is in blue, and they don't line up, okay? So it tells you that at least it's a very strong piece of evidence that there is matter that is not the gas, okay, and that matter, and moreover, notice that the dark matter, the blue spot, is also lining up with the galaxies. You see a bunch of galaxies, and the galaxies, just like dark matter, pass through during the collision. All right, see, here's the animation. So you start with 2 clusters. It's called the bullet because the small guy really acts like a bullet, okay? It comes in, hits the big cluster with high speed. You see that during the process, there's a segregation between the gas and the dark matter, and this is what we observe at the end of the day. Okay, piece of evidence number 4, the cosmic web. When you look on the larger scales of the universe, so what people do is we do simulations. We start with a universe that contains many, many millions of dark matter particles, put it in a computer, let them evolve through gravity, and this is what happens. Under gravity, of course, dark matter particles will attract to each other, and eventually this initially, which was almost perfectly homogeneous, evolves to this remarkable structure having these little clumps, and this is only dark matter simulation, so these little clumps will eventually be homes for galaxies, we think. And you see also these beautiful filamentary structures connecting the different galaxies. This simulation actually makes prediction, therefore, for how clustered we expect galaxies to be, and then on the larger scales we can observe, this fits beautifully with the data. All right, so let's do a summary. Remember, you're part of a jury. You have to make your judgment. Was that convincing? Was it not convincing? Okay? So I showed you, in summary, 3 main pieces of evidence. I've grouped a couple of them together. So the first piece of evidence was the cosmic, actually that was the last one. There was no preferred order, okay? I don't pretend to be a professional lawyer. The first piece that I presented to you, if you want, was this cosmic web and gravitational lensing, okay? And here I've included also the microwave background, which we didn't discuss. I presented to you galaxy clusters, and the third one was galaxies themselves. You know, you can make up your mind which of these is most convincing. Here's to give you an intuition for what I think is most convincing. Cosmic web and gravitational lensing is like having DNA evidence, okay? You find blood of the victim, you match DNA of the suspect, whatever, okay? It's very, for a cosmologist, for a forensic expert, it's like very clear that there has to be dark matter based on that. Galaxy clusters, it's like finding blood, okay? In the car of the suspect, at his house, okay? It's telling, but galaxies, on the other hand, it's like finding a glove, and it matches the person's glove, but it doesn't quite fit, you see? And it's enough to make you ponder whether you've got the whole picture right. Okay, so I want to talk about the conspiracy of galaxies. What I want to convey is, first of all, I believe in dark matter. I believe that dark matter is a particle. But I believe that on the scales of galaxies, our simplest notion of a dark matter particle that doesn't interact with itself very much and with ordinary matter, that picture has to be revisited. So what's going on with galaxies? First of all, galaxies are really complicated objects when you think about it. Because in galaxies, you don't just have dark matter, but you have stars, you have gas, you have all kinds of physics, which is very complicated. So that complicated physics should yield some pretty complicated looking objects. But in fact, galaxies are remarkably simple. Their rotation curves, which I explained to you earlier, the velocity as a function of distance away from the center, as we've said, is flat as you move out. And that's pretty regular. We see flat rotation curves all over the place with galaxies. Why is that? More importantly, and this may be a little subtle, but it's a very important piece of evidence, there is a scaling relation, an empirical scaling relation for galaxies, which works remarkably well, and we don't understand why. This is known as Tully-Fisher, because of Tully and Fisher. But really, many people have contributed to this. So let me tell you what this relationship is all about. What is a relationship between V, which is this asymptotic flat velocity that you see in galaxies, the total mass in ordinary matter in the galaxy. And that precise relationship is that the mass in ordinary matter is proportional to this asymptotic velocity to the fourth power. Why is this strange? It's strange because if you think about it, the velocity asymptotically should depend on how much dark matter there is, right? Why does that have anything to do in such a precise way to how much ordinary matter there is? It sounds like a conspiracy, right? The ordinary matter is a small component, and yet it dictates precisely the amount of dark matter there has to be further out in this precise way. And you see on the plot, it's a very tight relationship, okay? And that's not understood. But as I said, it's a complicated process. You have to model, if you're going to try to model this in the computer to understand where this comes from, what people do is the following. You assume ordinary dark matter that doesn't interact with itself. You can just think of it as just interacting through gravity, doesn't interact with ordinary matter. But you put on your computer that simple stuff with all the complicated stuff of stars, of gas, supernova exploding, black holes. This is just a partial list of what modelers have to put in their codes to actually simulate a real galaxy. They have hundreds of parameters, okay? It's a very complicated system. Now, what they do with the simulation is they actually choose those parameters in the best guess possible, but in a way that they can reproduce this beautiful Tully-Fisher scaling relation. The key point is the following. You see, if you go back to this Tully-Fisher relation, what was striking about it is not the fact that there is a scaling relation, but it's the fact that it works so well. In other words, it's so tight. You would expect, maybe on average it's this particular slope, but you'd expect points further out representing the fact that there's complicated physics going on, and it's not a perfect law. Whereas here it looks like almost it's perfect. And so indeed, when people do simulations, they find that the dots are the simulated galaxies, so with all the complicated physics, and what you should compare it to is the yellow band. The yellow band is observations, if you want. So what you see is striking. You see that the simulated galaxies are all over the place compared to this thin band which represents observations. Okay, so there has to be a conspiracy, in a sense, to explain this. There are other problems, and people disagree. Are they problems? Are they just, again, misunderstanding what the complicated underlying physics is? Let me mention a couple, and as I say, these are a matter of debates, but one of them is the so-called missing satellite problem. When you do simulations of dark matter only, I showed you one, with all these beautiful structures and these clumps, what you find is the following. You see on the left side, this is a simulated dark matter story. You see a big dark matter clump in the middle. That would be the home of, let's say, the Milky Way galaxy. You imagine this would be the home of the whole Milky Way. But you see surrounding it are these hundreds of little clumps, okay? And you wonder, those should also, in principle, be homes to smaller galaxies. So when we look around the Milky Way, we should see hundreds, in principle, of these small galaxies. And we don't, okay? We observe 30 of them. Now it becomes a question, maybe these lumps are there, but they were too feeble to hold on to their gas and to form stars, so they lost their gas. It's their own story, you can say. And this problem, one can make it even sharper with technical details. But anyways, it's one of the puzzles that's been around for quite a while. Secondly, you expect that around a Milky Way-like galaxy, notice that all these clumps are pretty much isotropic, right? They look pretty much the same all around the Milky Way. Whereas what we observe is quite remarkable. The satellite galaxies, so on the bottom plot here, I show you our Milky Way galaxy at the top, with the blue dots are the dwarf galaxies, the satellite galaxies around the Milky Way, those we observe, and those around Andromeda, our nearest neighbor, with its own satellites. And what do you notice about them? You notice that the galaxies that we observe, they're not isotropically distributed around the Milky Way or Andromeda. A number of them lie on these planes, these thin planes. Okay? And moreover, the Andromeda plane points towards the Milky Way. This suggests at least there has to be more physics than the simple picture above of just these clumps individually happily forming around the Milky Way. So these are things that some of us spend a lot of time thinking about. Again, it could just be conventional physics at the end of the day, but it's at least puzzling. Okay, so here's the bottom line. In my mind, this is not just conventional physics. It gives us strong hints about the nature of dark matter. Okay, so if you want, I think nature is singing for us, loud and clear, and we should be listening to what nature has to say about this. I want to tell you about a crazy idea. Totally radical idea, but at the end of the day, I want to tell you how I think about this idea. And it's called modified Newtonian dynamics. So this is a law that was proposed by Marty Milgram, shown here, an Israeli physicist, who proposed it more than 30 years ago. He studied galaxies, and he proposed this rather bold idea. So after all, when we say in the galaxy there has to be dark matter, we base that on the fact that we see stuff moving faster around the galaxy than it should. But we only infer this based on gravity. We don't see the dark matter directly. We infer this on... So what if, instead, there was no dark matter, but instead our law of gravity has to be revisited? Here's what he proposed. He proposed, okay, let's imagine there's no dark matter, and instead, Newton's law of gravity has to be altered when you go in a particular regime. And here's how it looks like as an equation. The statement is that when you transition to this new regime beyond Newton, it's when you go to very low acceleration. Okay, so that you have to think about it, right? Acceleration here, 10 meters per second squared, okay? This transition occurs at extremely low acceleration. You see the numbers, 10 to the minus 8 centimeters per second squared. That's all you need. That's the acceleration you need to keep a star far away in orbit in the galaxy. When you transition below that scale, all of a sudden, Newton's law of gravity gets modified. Instead of being the Newtonian acceleration, you see this particular square root form. It's the geometric mean of the Newtonian acceleration and this new characteristic acceleration. This sounds totally kooky, okay? But if you want, at the end of the day, it's a proposal, okay? So he goes ahead, makes this proposal, and starts looking at do galaxies actually obey this? And amazingly, they do, okay? So here are some actual fits of real galaxies, their rotation curves, and with this simple law, there is no dark matter to muck around here. You have a law which only involves the stuff you see, And with that stuff you see, you predict how these rotation curves should look like. And you only have basically one parameter, which is this characteristic acceleration. And it works remarkably well. Okay? Furthermore, this Tully-Fisher relation that we observed is an exact prediction of this theory. Exact prediction. Okay? And I could go into details. Actually, this sounds like a post-diction in the sense that you could say, well, he cooked up a law that fits those rotation curves. Not so. He actually predicted that some galaxies, in particular, if you look at the bottom right corner, that galaxy was not observed at the time where he made his predictions, when he came up with this idea of MOND, and he actually predicted that such galaxies should exist. Now, you can take different viewpoints on this. The conventional viewpoint, we have to distinguish empirical facts from theory. As an empirical fact, this works. So even if you believe that dark matter is this conventional particle that doesn't interact, blah, 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 your viewpoint is that I put in this simple particle, I put in all the messy physics of stars and gas and all that crazy stuff, this ought to come out. It has to come out because it works with the data, okay? You see what I mean? So you could say the extreme viewpoint is that, no, there is no dark matter. This law is fundamental, it's a fundamental law of gravity, Newton was wrong. Or the conventional viewpoint is, there is dark matter, it's a simple particle, and somehow when you put in all the complicated physics, this comes out. But it has to come out as an empirical fact, okay? This is not all roses, unfortunately. That law that was proposed by Milgram works beautifully well with galaxies, but it fails on other scales, which is why a big portion of our community chooses to basically ignore it, because it fails with these other pieces of evidence that I presented you as members of the jury. In particular, galaxy clusters doesn't do very well with galaxy clusters. And when you get to the cosmic web or the cosmic microwave background, also doesn't do very well on those scales, okay? And as I said, this was to me the DNA evidence for dark matter. So if you're going to mess around with microwave background in this cosmic web, as members of the jury, you start feeling uncomfortable, very uncomfortable. But as I said, it's true. That empirical law works for galaxies. I take the middle ground, okay? I'm in the middle. I don't think it's a fundamental law of gravity. I don't think it's purely some magic having to do with stars and cooling and supernova and stuff like that. I think it's telling us something about dark matter, that there's a property of dark matter that is such that this MOND phenomenon arises in galaxies. So I take the middle ground. I think there is both dark matter, and I think MOND, this modified Newtonian dynamics, is also there, but it's due to the fundamental properties of dark matter itself. So how do you do that, right? It's easy to say, but how do you put the two together? And in fact, as a scientist, you already should have pause at that moment, because if I tell you I have two phenomena, MOND and dark matter, and I'm going to put them together, you should start saying, well, okay, wait a minute. It sounds too complicated, right? Why can't we just get away with one? The proposal that I've been thinking about, and this is what I want to share with you, my research has been to think about the physics of superfluidity as precisely the ingredient that marries the two in a natural way. Okay? So this will be a unified approach to both this modified Newtonian dynamics and dark matter through superfluidity. What is a superfluid? Okay? What is a superfluid? Superfluid, the sort of poster child example is liquid helium. Here's liquid helium. Liquid helium, you cool it, it bubbles. Okay? This is just boiling. All kinds of things happen. Once you reach a particular temperature, 3 degrees Kelvin or so, its behavior completely changes. Okay? Did you see it stopped boiling entirely? When the temperature is lowered, at some point, it completely stops. Let me tell you what's going on. Okay? Normally, when you take a fluid and you cool it, eventually it forms a solid, right? That's what happens with water. And the reason is that you have molecules in the liquid moving around because of the temperature. They're jittering around. As you cool them, their jitter slows down and eventually allows them to bind into a crystalline structure, very ordered structure, and that's the ice phase, okay? However, you know from quantum mechanics that even at absolute zero temperature, atoms are not sitting still. They will have a quantum jitter, just due to quantum mechanics. What happens with a superfluid is that quantum jitter is enough to prevent the substance from forming a solid. Does that make sense? So the quantum jitter is enough to keep it into fluid, even at zero temperature. So liquid helium, you can cool it all the way to zero temperature, in principle, and it will remain a fluid. Now, you could say, this sounds very nice, thank you, Justin, but why in the world does this have anything to do with dark matter, right? It sounds like a crazy, why does dark matter behave like liquid helium? In fact, superfluids are not that strange of a beast. Of course, we never really see them in our day-to-day experience because our day-to-day experience is at much higher temperature than 3 degrees Kelvin. But in principle, there are two things you need to have a superfluid. People do it, for example, just with cold atoms in the laboratory. You cool down a bunch of atoms together, and eventually they can form superfluid. So really, the two conditions you need for superfluidity are the following. Why would it be that dark matter can be a superfluid? First of all, you need a lot of these particles. You need a lot of dark matter around in order to be dense enough in order to form superfluid. So if you want, the first condition to have superfluid is that you have a lot of atoms, you have a lot of dark matter. I say atoms because I think of them actually as dark matter atoms. But okay, so you need a lot of them. Now, we know the total mass of dark matter that we need, let's say in galaxies. So we know the total mass. So if you want to have a lot of dark matter particles, it means that each particle has to be light, quite light. So when you work out the numbers, it turns out that the mass of the dark matter particle has to be 0.1% the mass of the proton. Much lighter than what people think about when they think about weakly interacting massive particles, WIMPs, which are much more heavy than this. But people talk about other types of dark matter particles that have masses in that range. So it's not crazy. They just happen to be light particles. Secondly, they have to be cold enough. And dark matter is pretty cold, right? It's one of the properties. Dark matter, it just has to be in thermal equilibrium at a very cold temperature. Now, when you work out the numbers as to what, remember I told you for liquid helium it was 3 degree Kelvin, that transition. If you work out what would be the critical temperature for transition to superfluid state for dark matter, you plug in the numbers, doesn't have to come out with, it could be any crazy number, it turns out to be millikelvin. And that's interesting because in the laboratory, with cold atom system, millikelvin is actually a reasonable number. With lithium atoms, I'm not saying dark matter is lithium atoms, okay? Don't get me wrong. It's something different. But when you look in the laboratory and you take lithium atoms, you find the critical temperature is 0.2 millikelvin. It's not a crazy number, okay? It's another hint that maybe these things are actually some kind of dark atoms. Again, not made of ordinary matter, but some form of dark matter atom. Okay. So here's the picture we have in mind in that story. We have in mind that in the Milky Way, or around any galaxy, there is our dark matter halo in blue, but in the interior, there is a superfluid bubble where the dark matter really behaves like a superfluid, all right? That's the picture. Now, why does that have anything to do with MOND or explaining properties of galaxies? That's just a statement, right, that we think there's a superfluid phase. One thing, I should say one other thing. We're about to propose that, in fact, MOND has to do with this superfluid nature. Now, as we've said earlier, galaxies work beautifully well with MOND. Galaxy clusters do not. So that has to be explained, right? If I'm going to say something nice about galaxies, I also have to explain something about galaxy clusters. So here's the key piece of physics. The temperature of the dark matter is set by how fast they're moving in the halo. And so, if in the massive object that we're talking about, so in a galaxy, you can work out that the dark matter motion of the particles gives them a temperature of order 0.1 millikelvin. So below this critical temperature, you see. So in galaxies, you expect them to be superfluid, at least near the center. There's a superfluid inside galaxies. Galaxy clusters, as we've said, are much more massive. So a dark matter particle in a galaxy cluster is whizzing around much faster because there's more gravity there, right? There, you work out what the temperature would be for dark matter particles. It's 10 millikelvin, above the critical temperature. So in galaxy clusters, you see, galaxy clusters are hotter in this sense. And therefore, in galaxy clusters, you're not in the superfluid state. You're in this ordinary dark matter phase. And that's what distinguishes galaxies from galaxy clusters, okay? Now, I haven't told you yet why MOND comes out of the story, right? Modified Newtonian dynamics. Now, one amazing thing about superfluidity, once you reach superfluid state, like we saw with helium, liquid helium, what you noticed in the movie was that initially the atoms of liquid helium were moving all over the place. You reached the superfluid state and then they stopped, Why did they stop? The physics of this is remarkable. What happened, and this is really quantum mechanics, it's the most striking manifestation of quantum mechanics. Once you reach this critical 3 ° Kelvin temperature, what happens with the superfluid is that at that moment, the individual atoms of liquid helium are no longer independent entities. Does that make sense? They lose their individuality. Now they have, because of quantum mechanics, they cannot individually whiz around, which is why you see the boiling stop. They start behaving coherently, in unison, if you want. They have what are called collective excitations. You don't excite yourself independently. You have to, all in the room, create a wave, like we see in the stadium. And that's exactly what happens. It's a collective motion, just like the wave in the stadium. These are known as sound waves. These are the excitations of a superfluid, or phonons. Now, phonons, here's a video, okay? You see that they're moving just like in the wave in the stadium, moving collectively, okay? Now, there is one thing, this is for a particular type of solid, animation for a solid. There's one thing that is not captured by this animation. You see that the atoms, as the wave is moving, they're going up and down, like you would do in a stadium. The kind of wave we're talking about is not going up and down. It's moving sideways. We call this longitudinal wave. It's actually how the sound from my mouth to your ear is propagated. It looks more like this. You see that the atoms in the movie, each individual atom is moving back and forth, right? That's the red dot. It's just moving back and forth. But collectively, there is an overdensity which is propagating in a particular direction. That's the wave, you see, but each atom is only doing this. Unfortunately, this animation didn't capture the fact that they're sort of coherent. The other animation showed that they're coherent. So you have to, in your mind, combine the two, okay? So it looks more like an ordered thing that I showed you before, but the atoms are moving this way as opposed to that way. Okay, so these are the excitation of the superfluid. So in other words, in the galaxy, once you're near the center of the galaxy, I imagine, that's my theory anyways, that the dark matter particles are not whizzing around in the way you'd imagine them to be. They're not whizzing around. They're behaving like liquid helium, like a fixed, coherent bulk of stuff sitting there. And moreover, when you excite the dark matter, it doesn't excite it by having a particle whizzing around. It excites it with these coherent waves near the center of the galaxy. So completely different than that we normally think of dark matter as being individual particles. Now, the key idea of this proposal is that these phonons, and this requires some mathematical details, which I cannot show you, but that the superfluid phonons are actually responsible for mediating a force, and it's a MOND force, okay? I will give you a gist for why this may be true, but for the moment, just take my word for it that mathematically these phonons can mediate a force on top of gravity, which looks like MOND, precisely the square root form that we discussed, okay? Now, why does it have anything to do with MOND? And the reason is, it's really what got me, the process by which I came about to this idea, was really because of a mathematical analogy. You look at the theory mathematically that you need to explain MOND, and it looks like the theory precisely of those sound waves of a superfluid. In fact, it looks eerily similar to the particular theory of a known cold atom system in the laboratory. Not exactly the same, but similar in spirit, okay? So it's the mathematical structure that led me to think that, wait, maybe this MOND phenomenon is describing superfluidity, and dark matter can certainly be a superfluid. Now, as we said, it naturally distinguishes between galaxies and galaxy clusters. We've said it before, so galaxies are very cold, and therefore they will have a superfluid, and therefore there you'll expect to have MOND behavior. As we said, this explains these beautiful fits of rotation curves. It explains why you have this conspiracy of Tully-Fisher. It comes about because of the superfluid nature of dark matter. Whereas in galaxy clusters, as we've said, galaxy clusters are much hotter. There is no superfluid phase in the galaxy cluster, and therefore no MOND. I want to qualify this because this will be important later on. When I say there is no superfluid, it's not quite true. There is a little bit of superfluid near the very center of the cluster, because there you don't have much mass, and so therefore temperature can be cold. This will be important later, okay? So near the center of the cluster, you have a little superfluid bubble just surrounding the central galaxy in the cluster. But for most of it, it's all ordinary dark matter. Imagine our little bucket of liquid helium, which we cool down, so now it looks nice and still. And imagine you start rotating the bucket. Now, when you rotate a bucket of water, water rotates with the bucket. Liquid helium does not, actually. It will remain still. But at some point, if you spin it too fast, what will happen is something has to give, okay? It cannot stay still. And what it does, instead of starting to spin homogeneously as a whole solid, as a whole liquid, what happens is it starts forming vortices, little vortices inside the fluid. And that's what represented in these sequence of pictures. As you spin it faster and faster, vortex is exactly like your toilet flushing, right? It's things moving around circularly. And you see that you develop more and more of these vortices as you spin the fluid faster. Now, the galaxy itself is spinning, right? The dark matter in the galaxy may well have its own spin. And therefore, if it's superfluid, it should not spin homogeneously like a ball. It should start forming vortices. In fact, just one more thing. This is actually a beautiful experimental result with liquid helium by a group at University of Maryland. They show actually they're able to map these vortices. You see them as lines. What I want you to see from this graph is that these vortices are not just standing still, boringly, whizzing around. They're actually interacting, they're combining, they're reconnecting, etc. It's a very dynamical system, these set of vortices. It's very cool, okay? So therefore, the picture we have in mind as one possible observational signature is that, in fact, the dark matter in the superfluid bubble should have all these little vortices. Now, if you ask, great, how come I don't see them, okay? First of all, there are many of them. If you estimate how many vortices there will be 100 of them within the size of the solar system. But they're very small. In thickness, they're like 1 millimeter. So the mass that they have is very small, okay? So it's not clear whether you can easily see them. For example, you can say, well, if they're there, they're massive, I should see that, I should feel their presence in the solar system. They're very feeble lines of density, okay? So we're still thinking about how you might go about finding those vortices, but they're in principle there, if you believe this idea. Now, a very interesting, and you actually saw this in the movie I showed you earlier about this beautiful cosmic web in blue and things coming together and so forth, forming these filaments. What you saw there, if you looked closely, was actually that these little lumps, right, connected by filaments, some of them were actually merging together. They'd come together, they'd merge, form bigger lumps. That's actually a very important part of our understanding of the formation of the structure in our universe, is that small lumps can come together and form bigger lumps. Let me show you this, and I'll tell you the physics of why this happens. It's actually it's actually very interesting why these galaxies merge. But I'm going to show it to you in the most dramatic way, okay? By showing you the future of our own galaxy, the Milky Way. As we know, it's on a collision course with Andromeda, our nearest neighbor. So you can ask, let's look in the future, okay, billion years into the future. We're on a collision course with our friendly galaxy nearby, and here's what happens, okay? So here's a movie, a simulation of what's going to happen with the Milky Way and Andromeda. And you see they're on a collision course, but notice what's going to happen. They come together, they start sloshing together as this happens, and eventually come back together, slosh again, and eventually they relax into a single galaxy, okay? This is our fate, okay? And remarkably, we'll survive this. This is our future. Now, notice that this was a very interesting movie. In fact, let's imagine this for a moment. If Andromeda and the Milky Way were just 2 points, right, and they came together by gravity, one thing that could very well happen is they would just slingshot past each other, right? There's no reason why they should merge to something together. Whereas in the movie, what you saw is they come together, they want a slingshot, but they kind of like slosh around and they come together. It's as if there was some friction that's kind of sloshing them and bringing them together. Does that make sense? If they were 2 particles, you would expect them, okay, there's no reason why they might form a bound state, they might start, but why would they merge together at the center? That usually think of friction. That's a very interesting process, okay? And it has to do with the fact, of course, that they're not particles. They're made up of a whole bunch of particles. You have to think about a lump of particles coming together with another lump. What happens then? It's not 2 particles, it's a bunch of particles together. It's a process known, a very well-known process dynamically, known as dynamical friction. Goes back to Chandrasekhar. So dynamical friction, it's a form of, there's no friction fundamentally, it's just gravity, but it's a form of effective friction that comes about from the fact that there are many dark matter particles around in these galaxies. Let me illustrate to you. It's a very simple process. So imagine at the top, imagine you have a mass m, which is passing through a gas of other particles. This mass m could be itself a particle, okay? But let's just imagine, to illustrate it, it's a particular body that's moving through this gas of particles. At the first instance, of course, it attracts gravitationally the particles around it. Then it moves away, but those particles then moved in because they were attracted to that body initially. That's what you see in the second plot. You see there's a little bit more particles on the right in the second slide, and that's because the object attracted those particles in. But as a result now, there's more dense particle, there's more mass, if you want, on the right, on the right than on the left, you see? So as a result, there's a force now, a net force, bringing the mass back to where it came from. Does that make sense? Let's think about it again. So you start with the top. This particle is moving around. At the first instance, it attracts the particles around it. Particles come in. Now the mass has moved, but now there's an overdensity of particles. That attracts it back, right? Which means it slows it down. And so on and so forth. Now, in the second slide, it attracts also neighbors, brings them down, attracts them back, okay? So this process is precisely the process which slows things down and it's what leads to the merger, eventually. We call this dynamical friction. Notice that it critically hinges on dark matter particles being individual entities, being able to move around, rearrange themselves independently. So you see they come about, and now as they come about, now the sloshing is beginning, and that's again the dynamical friction. And it leads at the end of the day to the merger. Okay, what happens with a superfluid? The hallmark of a superfluid is that it has no viscosity. What's viscosity? Viscosity is the resistance of a fluid to flow. You notice, you say, honey is more viscous than water because it's harder to pour it out of the bottle. That's because it resists to the flow. In fact, if you think about it, and maybe you've had that experience, imagine you took your bottle of honey and you punched a little hole with a needle at the top of your honey bottle. You turn it upside down, and you know what happens? Nothing will flow if the hole is too small. And that's because of viscosity, you see? Water would come out because it's less viscous, but honey will just stick there, okay? Notice what's going to happen with the liquid helium. I'm about to show you a movie. Here's again our favorite bucket of liquid helium. Initially, it's not going to be superfluid. At the bottom of this bucket, they did exactly what I said. They punctured a bunch of tiny little holes. Just like honey, when it's normal liquid helium, nothing's going to flow. But when it reaches critical temperature and becomes superfluid, you'll see stuff starts to pour through the holes, even though they're extremely tiny holes. Okay? Let's watch the movie. Initially, it bubbles, nothing goes in, becomes superfluid, and now you see at the bottom, you see stuff pouring out. Right? Let's see it again. You see, initially, nothing comes out, cool it down, stuff starts pouring out. And that's the hallmark of superfluid, the lack of the zero viscosity. It can flow through anything, no matter how small the capillary, no matter how small the tube, it will flow through it. Okay? That's a superfluid. Now, what it means in practice, of course, I should qualify this. It's no viscosity at absolute zero temperature. If you're at a little bit non-zero temperature but below critical temperature, there will be a little bit of viscosity, okay, in the fluid. But in any case, what we expect for us, if you think about the dark matter fluid, superfluid, is when you had these galaxy mergers, you expect there will be less dynamical friction, less viscosity between the galaxies as they're moving together. So it will change a little bit how galaxies merge, you see? It will change. They'll still merge, right, because these things are not at absolute zero temperature and so forth, but it will be less dramatic than what you saw with Andromeda and the Milky Way. Less dynamic. Now, why is that a good thing? This is pretty subtle, but let me give you some, you guys are jury members. You want to know evidence for this crazy idea. So what are the evidence that leads me to think that less dynamical friction is a good thing? Less friction in the dark matter is a good thing. Here's one of the dwarf galaxies, satellite galaxies around the Milky Way. It's known as Fornax. Now, here it is. As you can see, it's a very feeble galaxy, has very few stars compared to the Milky Way. And around it, I've circled some points, okay? These are clusters of stars. We call them globular clusters. They're in orbit around Fornax. Now, if you believe ordinary dark matter, these little clumps of stars in Fornax are swimming in the dark matter halo. You see, they're swimming in the dark. Dynamical friction, just based on the little animation we saw earlier, dynamical friction should have led these clumps of stars to go towards the middle, towards the center of Fornax, precisely for the same reason that our galaxies merged. And they don't. They just happily stay where they are. They're not moving to the center. They're prevented. They're orbiting, but their dynamical friction is not bringing them to the center. Now, conventionally, you could interpret this as maybe the dark matter halo doesn't extend as far, or so maybe the dark matter distribution is different than we think it is. But in my case, this is explained quite naturally. These clumps of stars are swimming in the superfluid. They're not feeling the viscosity. They're not feeling the dynamical friction that would bring them to the center. That's how I explain why these guys are staying where they are as opposed to being dragged to the center. Here's a galaxy cluster. And remember, I told you galaxy clusters don't have a superfluid except near the center. Okay? Here's a galaxy cluster. What you see near the center, you see this bright yellow region. That's the brightest region of the cluster, and it encloses the brightest galaxy in the cluster. But notice, if you squint your eyes, you actually see 3 little dots within the yellow region. You see that? Those are actually 3 galaxies. They're so close to each other that if you believe they have this dark matter halo around them, their dark matter halo are basically overlapping. So now you can ask, wait a minute, you showed me a movie of 2 galaxies merging, and when their halos were sort of overlapping, they merged. Why these guys near the center of the cluster haven't merged? In principle, their halos are overlapping. That's very interesting. It's a puzzle. People, you can come up with. But again, in my case, this is explained. Yes, they have halos of superfluid, but they're superfluid. So the merger is very different. They don't feel the same kind of friction that ordinary dark matter would give them. Okay? Anyways, hallucinations. Hallucinations from a crazy theorist. Now, some other very interesting observational properties of superfluids is when actually superfluids collide, what actually happens. So people do that in the laboratory. So here's what happens. You take 2 lumps of superfluid, bring them together, okay? You see, eventually, they come out, and notice that they came out, and they retain their shape that they had initially, right? So this is, again, a hallmark of the fact that superfluids pass through each other without any dissipation, without any friction. They're happily passing through each other. But what did you see in the middle when they were overlapping? You saw fringes. You saw these lines, right? Let's look again at this movie. You see they come together, and when they're overlapping, you see what we call interference. You see dark spots and bright spots. And that really is due to the quantum mechanical nature of these guys. It's the fact that they're quantum mechanical that you see these interference, much like we see with the 2-slit experiment as one of the evidences for quantum mechanics. So when people simulate, so people have done simulation not of my superfluid, but a related type of dark matter superfluid. This is, again, like the blue movie I showed you earlier with formation of galaxies. I'll show it again in a second. But you see, again, these lumps forming. These are like the galaxies eventually. You see them coming together, and you see the wiggles, no? You see them, the ripples around them? Those ripples are the same interference effects that we saw with the experimental lumps coming together. Okay, let's see this again. So you see they come together. They form, first you form the lumps, you form the homes that will later be galaxies, and then they start coming together because of gravity. And as they come together, they form these fringes, okay? Could you see this? Well, there is actually there are known structures around elliptical galaxies. There are these beautiful rings. They have, truth be told, a conventional explanation within standard dark matter. But this kind of interference that we're discussing between superfluid could have another contribution to these kind of shell-like structures that we see around elliptical galaxies. Perfect. So I want to leave you with some thoughts. I told you, I brought you on a journey. The first thing that I want you to take home is that dark matter as a particle is highly successful. It's most successful in the DNA piece of the evidence. It's successful on the largest scales in explaining the cosmic microwave background properties, the cosmic web, gravitational lensing. So all the large-scale stuff works exquisitely well. Meanwhile, this MOND empirical law works beautifully with galaxies. Doesn't work well on the large scales, but on galaxies it works amazingly well. You should think of it not as a theory, but as an empirical fact about galaxies. So is there a way to marry these two ideas together without giving up altogether the idea of dark matter, still keeping the successes of the dark matter, but then incorporating this MOND behavior not as a miracle of star formation and so forth, but as a real fundamental property of dark matter? And the idea that I presented to you is something that I've been working on actively, is the idea of a dark matter superfluid state. As I told you, it's not crazy in the sense that we know with cold atoms, you cool them, you make them dense enough, they form superfluid. So if dark matter is of that type, there's enough dark matter and it's cool enough, you will form a superfluid state of dark matter. And in this picture, really dark matter as a particle and as a MOND phenomenon, it's really two sides of the same coin. They're just different phases of the same substance. It leads, I think, to eventually a rich spectrum of predictions, in particular for these mergers of galaxies, as we saw. Dynamics should be quite interesting. And I want to leave you with some open questions that I think are fascinating and that I'm thinking about actively. What would be a precise analog? I told you it looks like cold atoms that people study in the laboratory. I told you mathematically it looks similar to the theory that describes those cold atoms. So can we find an actual cold atom in the laboratory whose properties would be identical to the kind of superfluid I need for a MOND? Okay? Does that make sense? If you can find such a actual superfluid in the lab, you could, in principle, in the laboratory, start simulating galaxy collisions with cold atoms. Okay? That's the ultimate dream. Can you find such an analog in the laboratory that would allow you to study galaxy mergers and so forth? And of course, the elephant in the room is dark energy, right? I didn't discuss dark energy, but dark energy, which makes up 3/4 of the energy budget of the universe, is itself a big mystery. What is dark energy? Ideally, it would be very nice, if dark energy could somehow fit nicely, holistically in this picture. Maybe not in this particular superfluid picture, but in general, as some other phase of the dark sector, not as opposed to just another ad hoc component we add to the budget of the universe. Thank you very much.